Welcome to week 41 and the lectures for the machine learning course. And the aim this week is to start building up our first code for a neural network. So one of the aims, for instance, with project number 2 is actually to be able to write our own simple neural network code. This means that we are going to discuss things like the feed-forward part of a neural network and the back propagation algorithm. Then later we are going to play a little bit around with this feed-forward neural network or multi-perceptron layer model, as it's also called. And we are going to look at how to solve differential equations with neural networks. So this will be the topic for the next session. Now, before we move on, one of the things which we want to bring back again is the famous back propagation algorithm. And if there is an under-communicated topic in the machine learning community, is the connection between the back propagation algorithm and what we have met earlier in connection with the discussion of gradient descent methods and automatic differentiation. So automatic differentiation has two specific modes, one which is called the forward mode and one which is the reverse mode. And the reverse mode is actually back propagation. So we are going to try to make some links between auto differentiation or automatic differentiation as we call it and the back propagation algorithm. So we are going to repeat some of the basic elements first, and then we are going to dive into the architecture of a neural network. Now in the slides here which you have, and in front of you now you have the Jupyter notebook, which is the one we will spend most of the time on. The first thing we're actually going to do now is to have a review of the back propagation algorithm. And there are also some videos which you should feel free to look at. There's an excellent one on the basics of neural networks, and then there's another video on the back propagation algorithm. Now before we move on, let's go back to the whiteboard and take a closer look at the back propagation algorithm and the basic setups of a neural network. So we are going to switch over to the whiteboard, and let's try to do that as quickly as possible and try to bring up the basic features of a neural network. So if we now take a kind of more overarching view of what we are going to do in project number 2, then we can set up a kind of a list of the important elements or components of a neural network. And this kind of graph which you're going to see, or kind of overarching setup, is something which you will see again when we are going to deal with convolutional neural networks and also with recurrent neural networks. Now we are going to use the acronym as NN, and since we are dealing with neural networks in plural, we're going to have a subscript S here. Now, sometimes you will see this as an ANN acronym, which means artificial neural network. Sometimes you will see this as an FFNN, which means feed forward neural networks, but I will just use neural network as a shorthand. So one of the things which we need to set up then, when we are looking at the important components, is the architecture itself. And this is something which we sometimes will refer to as the model, but let's just call it the architecture. So this is an important element or model. So if you think back to what you did with linear regression and logistic regression, then we made a model for a specific function which we wanted to reproduce, and that could be something like a polynomial. That would be our model. It could be another function parameterization of the data points we wanted to reproduce. So what we are going to have as important ingredients here is the number of hidden layers. This would be part of the architecture and the model. Then within a hidden layer, we will have a width of the hidden layer, and the width of the hidden layer is something which is defined by the number of nodes in a given hidden layer. Hidden nodes in a specific layer. So when we are now going to write our first code for a neural network in connection with project number 2, these are things which we have to define before we start running the calculations. And then we will have to decide whether we want these layers to be fully connected, and that is the standard, the default when we are setting up a neural network. So that means that we have fully connected layers. This means that the nodes from one layer connect with all the nodes in the next layer. When we are coming to convolutional neural networks, you will see then that it's pretty common then to reduce the connectivity in order to save the number of mathematical operations which we end up having to do. So this is the type of connections which we are going to make. And then we need also to decide upon the type of activation functions. And that gives us a set of functions which we can play around with. And we have already met some of them. There is a plethora of activation functions in the machine learning community. So the functions which we have made, which we looked at last week, is something like the sigmoid function. We had a tanh. We could even have a simple step function. We met the family of rectified linear units, so ReLU functions. We met the family of ELO function, the exponential linear units, etc., etc. So there is a plethora of these functions which can be used, and many people will, when they're running and setting up a neural network calculation, they will actually use these as a kind of parameters. But we will put them under the slot of architecture or the model. So we just outline this one. This is the first part. Then the next part which we need to deal with is the so-called cost function and optimization. So we have to decide whether we are doing a classification problem or whether we are doing a regression type of problem where we want to fit a specific function. So we will have then cost function and optimization. So this is the other, what we might call overarching element of a neural network. And actually this applies to all of deep learning. And when we say deep learning, it has to do with a number of hidden layers. So the more hidden layers you have, the deeper the network. And the width of the network is given by the number of nodes which you would have in a given hidden layer. So the cost function is one of the types of so-called parameters or parts of the model which we are plugging in. So we will need to specify the type of cost function or loss function. Cost or loss function. And we've met also other names for it, like the risk function or the error function, etc. We need to define the type of regularization we want to deal with. Whether we want to have a norm 2 regularization like we had in ridge regression, or if we want to have a norm 1 or other types of regularization terms. And that introduces a set of parameters. So we've also been calling this regularization part for the shrinkage part or just the hyperparameter part. Next, what we need to define, and this is equally important, and it comes back to the backpropagation algorithm, we need to find which kind of gradient descent method we want to deal with. So the gradient descent method, so we could have gradient descent, just a plain gradient descent, and we would then have methods like momentum gradient descent. We could have an adaptive learning rate. We could have a ADA-grad method. We could have the root mean square propagation, etc., etc. Next, we would need to deal with the stochastic gradient descent, which is another of the methods which we are going to encounter in specifically in project number 2, where we're actually going to write our own gradient descent method. So we have an SGD, which is the stochastic gradient descent, and here we will need to define something like the number of batches and the step size for the learning rate, step size. And in our case, the step size is actually what we normally call the learning rate, which is one of the parameters which we have. Now, what you could call this part for, which we call cost function and optimization, we could think of this in a general term as the optimization choices. So you could now, if you want to label this with a common denominator, we could call this for optimization choices. And as I mentioned in one of the lectures, I mean, some people get frustrated because there are so many parameters and so many choices. Now, one of the things we're going to see a little bit later is how do we actually, and what kind of strategies do we opt for when we want to do the optimization. And it's pretty common, since the regularization parameters tend to give a heavy weight on the final, let's say, mean squared error, and similarly with the learning rate, then it's pretty common to actually tune these parameters first. And then when we reach something which looks like a optimal mean squared error or an optimal accuracy for dealing with a classification problem, then we could try to tune the other parameters and see whether the results are stable or not with respect to tuning these parameters. Learning rate plays a very important role because that defines the gradients and the way we deal with the gradients. So we also have other specifics, which we are going to mention a little bit later. And this is something like pre-processing. To give you an example, suppose you have performed a pre-training of a neural network, where you, for instance, trained a function to be reproduced by a second-order polynomial. Then you've already found some optimal parameters, which you then could feed into the new training of a new neural network. And you will often see that in imaging, that you will have a huge set of images which use a pre-trained network. So you could have a huge collection of cats and dogs, for instance, and then you would train a neural network to reproduce this exactly. So you have a perfect accuracy. So all dogs are correctly classified, all cats are correctly classified, and then you could feed into this network a new set of images of cats and dogs, and then you could keep training. So having trained already a network is something which is often used in training new data. As another example, if you are running an experiment and you have lots of noise in your data, what is pretty common is to pre-train the network or pre-process the network with the results from a simulation. So you have a simulation of a specific physical process, and that physical process which you simulate may not have any noise in it. So that means that you have a kind of a pre-trained neural network, and then you would apply this to a neural network problem where the data have lots of noise. That is a way to pre-process. There are other topics which we need to deal with, and that deals obviously with the way we initialize the parameters. So this pre-training or pre-processing is something which is often used. So the initialization is a common topic which we need to deal with. Then we have techniques by which we can improve the convergence of the gradient descent method. So we have something like dropout, which we are coming back to. We have topics like batch normalization. So these are all kind of ingredients of the gritty-nitty fine-tuning of a neural network. So there are many, many such topics. And if you go into the textbook by Goodfellow et al., and you look into chapters 11 and 12, you will find many of these topics being discussed. So I'm just writing etc. here. Now, what we need to do now is just to remind ourselves a little bit about the setup of a neural network. So last week, we looked at the basic setup of an NN and the mathematical expressions which we end up dealing with. So we're going to use that one to refresh our memory. And then when we've done that, we are going to remind ourselves about the back propagation algorithm. And when we've done that, we're going to make some links with automatic differentiation. So the typical feed-forward stage is the stage, let's just write this down here, of an NN. So we have what we call the feed-forward stage. And we are now going to write this in a more compact way. So we have the input layer, and we rewrite the input layer simply as this circle, and then we have a vector x, or it could be a matrix. So we don't need to specify that now. So this is the input. In the example of an image like the handwritten numbers, which we're going to look at a little bit later, then the data which we put in or input to the network, they would be represented by the pixels of an image. So if you have a large image with 200 times 200 pixels, then you would then feed in 40,000 points. Now this is then fed in to a first hidden layer. So we would typically label this as an H1. And each one of these layers has a specific width. And to this specific input here, we have a set of weights, which we label as a W. So this is normally represented by a matrix with unknown parameters. And in here, we would also feed in what we call a bias. And we just rewrite this one in terms of a superscript, which refers to layer number 1. And then we would have a series of nodes in here, and each node gets an input. And this input here is an input which we would write as a z of I, and this is a specific node j. So let me highlight it a little bit. So this is a z of layer 1, hidden layer 1, and then it is a node number j. And each layer can have the same number of hidden nodes, or it can have different number of hidden nodes. And this becomes a parameter in your architecture and defines your model. Now what we did next then is that each of these inputs to the hidden node, they are modulated by the so-called activation function. And this activation function produces an output. So this specific node here produces now an output, which we labeled via the function sigma. So we would have a sigma in layer 1, and this takes as input this zg from layer 1. And we wrote this, and let's change color a little bit so we don't confuse you too much. So we would label this as a j of 1. So this is the input, which is now modulated by a specific function, and these functions are called the activation functions. And in general, what we have then is that when we collect everything here, so these outputs from layer 1 is something which we last time labeled as an A, and this becomes a vector now, of length and the number of nodes which we have in the hidden layer. Alternatively, we would also write this as a sigma 1, which now takes as an input all the variables z1 here. And this is the same as an A of 1. So these were different ways by which we labeled the quantities of interest. Now, these outputs, they feed in to the next hidden layer. So they feed in to layer 2 here. So we have an H of 2. And now we are going to be a little bit sloppier. So we have a new set of weights. We have a new set of biases. And then this produces an output which we are going to write in a more generic form. So this would be a sigma of 2. And this takes as input all these variables z. And that produces an output A of 2. And this continues all the way to the final layer. And we label the final layer as, so we would now have a of L minus 1. This is L is the final layer, this is the output layer. So we have the output layer. And this would be an H of L. And that produces, so we just continue along this line. So this produces a new output. So we could have just one output, or we could have 2 outputs, we could have 10 outputs. This depends on the type of problem which we're dealing with. So we're just going to keep this in a pretty general form. So this will be a sigma of L, and this takes as input Z of L, and we wrote that one last time as an A of L. So this is the output which the network produces. Now this output goes into the cost function, C. Or if you use the label L for the loss function, you would replace the C with an L. So this is the cost function which we want to optimize. And then this receives as an input the target values as well. So these targets are the outputs which we want to reproduce. So this is a setup of a feed-forward neural network. We would initialize the weights and the biases, and then we send our signal forward, and at the end it produces an output which is modulated by all these functions. So what happens then is that the quantity which we previously have labeled as a y tilde, this is the output of our model. So keep in mind now that the model is the neural network. This is the same as this A of L, and this depends now on the input values and the parameters theta. So these parameters theta, just to remind ourselves of that, so these parameters theta, they contain all the weights and the biases which we need. So we need weights for the first layer, the biases for the first layer, and this goes all the way up to the final layer, and finally also the biases for the final layer. So these are the parameters which we are going to optimize with a back propagation algorithm. So what we do then is that we this quantity which you see here is something which we can rewrite in terms of the activation function which we have in the last layer. Now this receives as input the output from the previous layer, which is given by this L minus 1, and this goes all the way down to the next layer, L minus 2, and it continues till the first layer which we have, which now contains X multiplied with W1 plus this B of 1. And then we have all the different parentheses here. So this is essentially the function which ensures that we have this non-linearity, in the sense that we have these non-linear functions at every single layer, and they produce an output, and this output is fed into the next layer, and this goes on till we have the final output layer. And then the cost function, if we are doing a regression problem, like we've been doing before, could now be 1 over n, and then we have the norm 2 of t, the targets, minus the values of the output in the final layer. And this is norm 2 squared. So that is a typical activation function. Now in neural networks, what we have then is the so-called backpropagation algorithm, which is the way by which we actually train the parameters of a neural network. So we have the backpropagation algo. And what we are doing in this specific case is that now we take the output from the last layer. So we calculate the cost function. So we've calculated that one. So we calculate its derivatives. And we are using these derivatives now back again in the input to the last layer. So this will be a Z of L. This feeds in to the last layer, L here. So we have the parameters, the weight parameters, L, and then B of L. And this is fed now all the way back till we reach the final layer. So the training by calculating the gradients is something which is done by back propagating the various gradients using the chain rule, and then we have an equation by which we can train the weights and the biases in the different layers. So this proceeds till we reach the final layer. So we would now have a sigma 1 here, which now feeds in to the first layer, which now contains W1, and it contains B1, the parameters, and this is then fed back till we reach the last layer, and then compared with or modulated with the value X. Then when we've done this back propagation stage, we then repeat the feed forward stage. And this goes back and forth with a feed forward step and a back forward step till our cost function doesn't change by a certain value. Now, one of the things we have to keep in mind, and which is very important when we deal with the training of the neural network, is that the gradients at each layer, they do not need to vanish like we did with logistic regression and standard linear regression. And the reason for that is that because if the gradients disappear at an intermediate layer, then the training will stop and the neural network just ends. And that means that we may not have reached the optimal value for the cost function. So ideally, we want this cost function to be 0 if we are dealing with linear regression. If we are dealing with a classification problem where we are looking at the accuracy of a specific model, then we would clearly like to have the accuracy to be equal to 100%. Now, so if you now look at what we have here, we need now a model or way to train the weights and the biases so that at the end we have the optimal cost function, which then clearly minimizes the difference between the input and the output. And when we do this, there are many ways by which we can actually look at the problem and the complications. So one of the things which we are going to discuss a little bit later is actually the initializations of the weights. And this is something which is a very delicate topic, because if the weights are initialized wrongly, if they are way too small, then the training may stop. Then we have things like dropout and batch normalizations, which are ways to, certain way we could say these are ad hoc ways of hindering that the network stops training. So a typical kind of ad hoc rule which is often used is that if the gradient becomes too large, which may happen, then we just cut off the gradient and we go back to a previous value. This is done in order to avoid exploding gradients. So one of the problems in the training is a vanishing gradient, but clearly another problem could be exploding gradients. Now, if you now think of what we need to do, if you look at the derivatives of the cost function in a previous stage, and this is where the chain rule comes in. So if we now look at the basic operations which we are going to do now with the back propagation algorithm. So the back propagation, what we in essence end up having to do, and now I'm going to use a common denominator for the weights and the biases in terms of this parameter theta. So what I will need is the derivative of the cost function in the previous layer, so d theta of L minus 1. And if I use the chain rule, this is something which I can rewrite in terms of the derivative of the cost function so this is the cost function which we've calculated in the final layer. So I can calculate the derivative with respect to the output in layer L. So I would then have a d sigma of L and then a d theta of L minus 1. So this is one of the equations which we set up last time. And in our case, we can replace the sigma with the output A. So an alternative notation, which we also use. We didn't use the sigma notation when we looked at the calculations last time. So we could simply rewrite this as a d of A of layer L. So we take the derivative of the cost function at the final layer. And then we use the chain rule repeatedly to obtain the values for the derivatives as we step back. And then we have a d of A of L. And this is with respect to the parameters in layer L minus 1. Now we started by calculating the derivatives in the first layer. So that means that when we move on here, we would now need the derivative of the cost function in layer L minus 2. And this is something which we then can repeat again with the application of the chain rule. So we would have an A of L, and then we have a d of A of L, and then we would have now d of A of L minus 1, and then we have a d of A of L minus 1, and now we have with respect to the parameters in layer L minus 2 here. And what you see now is that the term which we have here, this specific term, is the same as the term which we had here. And now you can see the general pattern here, and the general pattern is something which would continue as we move on. So that means that when we reach a specific layer, lowercase l, so d theta of L, this is something which then would be given by dc of dA layer L, and dA layer L of dA of layer L minus 1. And this goes all the way up to the final one, where we would now have a d of A of layer L minus 1, and then we have a d of A of L, and then finally we will have a d of A of L of d of theta of L here. So this is something which will just continue along these lines till we have the final, oh sorry, I actually think I wrote it wrongly here, sorry. I started the wrong way here. Let me just wipe this out here. I put the wrong subscripts and wrong indices. So we would start with a dc d of A of L, and then we have a d of A of L of d of A of L minus 1, and this continues all the way to d of A of L plus 2, and then we have a d of A of L plus 1, and then we have a d of A of L plus 1 of d of theta of L. So this would be the basic steps which we would have in the calculation of the backpropagation algorithm. And that gave us a set of equations. So we had 4 equations which we would need to implement. So the backpropagation itself is just a simple application of a feed backward stage where we calculate the derivatives using the chain rule. Then when we have the derivatives, we would then plug them in our favorite steepest descent or gradient descent or stochastic gradient descent method. That means that when we have these derivatives, we will go back and update the parameters in an iterative way, and these parameters would then give us the via the gradient descent method, they would now give us the new weights and biases for a given layer. Now before we move on, and this is something which many of you may wonder, is why do we do this backward propagation stage instead of just doing a feed forward stage and calculate the derivatives? Now there is a nice link And this is really an underestimated part of machine learning. And actually, these were fields which were living in a separate lives almost before people actually realized the connections. And when people derived the backpropagation algorithm, this was just a way of calculating the derivatives and obtain the training of the parameters in an efficient way. And this is very much linked to automatic differentiation. So let's take a short dive into the field of automatic differentiation. We're now going to take just a small step aside and link this discussion of the backpropagation algorithm with automatic differentiation. So automatic differentiation plays a central role. And one of the reasons why we use automatic differentiation is that by applications of the chain rule, we can actually get numerical derivatives to numerical precision. Now, the standard formula for calculating derivatives, which are often based on finite difference equations, they can, when we now make the step sizes smaller, they can actually lead to a loss of numerical precision. They also tend to be less precise due to this, but they also tend to be more computationally expensive. And the standard differentiation algorithms, which are based on finite differences, are normally avoided in this type of calculations. You may ask yourself, why don't we use symbolic manipulations? Now, symbolic manipulations can often lead to unwieldy formula. They can lead to, unless you can simplify the equations, it can actually lead to derivatives which are very complicated and time-consuming to evaluate numerically. You could also obviously do the derivatives by paper and pencil, like we did with linear regression, where we had a simple equation for the cost function, and it was easy to set up the derivatives. Now, however, this is something which becomes time-consuming if you have more complicated functions, and it's very error-prone because you actually have to calculate these equations by paper and pencil, and then you have to program them. And the programming stage is something which also can lead to errors introduced by us, in the sense that we do not write the correct expression, which is very easy to do. So automatic differentiation is actually based on this kind of graphical image where you calculate intermediate quantities and you use the chain rule. So let's now try to look at one example here, a simple example, and then we move on to a slightly more difficult example. So suppose we take a function f of x, which is given by the exponential with an argument given by x squared. And we obviously know the derivative here. So f derivative of x is simply 2 times x multiplied with x, the exponential, with x squared. Now, we can now, when you're looking at the calculations here, there are many ways of doing that. And the most common one is actually to define some intermediate quantities. So if you look at the derivative, you can speed up the calculation of that one by calculating some intermediate quantity. So it would be natural then to define two intermediate quantities. One, which is a, which we simply write as x squared, like this. And then we define a new quantity, which is b, which is the exponential, which takes as argument a. And if we now look at the derivative then, what we would have is simply this 2x times the exponential of a. So if we have pre-calculated the exponential of a, it means that the calculation of the derivative, if we now have pre-calculated the exponential of a, because we need the function f of x, that means that in the calculation here, this is pre-calculated, so just a constant b. So we have 2 times x, which is one floating point operation, and multiplied with b, which is another floating point operation. So that means that calculating the derivative with these intermediates is something which gives rise to only 2 floating point operations, because we have already calculated the value here. So we need simply to perform 2 times x and then multiply with b. Now, if we have a more complicated function, as you will see in the next example, this can lead actually to a considerable reduction in the number of floating point operations. So if we now were to calculate these quantities without thinking, so what you would have then, if you look at this function, you would have x times x, so that's one floating point operation. If we now democratically assign one floating point operation to the calculation of the exponential, which is not true actually. Actually, the exponential requires more floating point operations, but let's say just one floating point operation. That means that here we would have two operations, x times x, and then the exponential function calculation. So we have two flops here. Now if you go to the next case, if we now recalculate this one, we would have two floating point operations here, and then we would have a multiplication, which is another one, and then new multiplication with 2 times x. So if we were not to think here, that means that we would calculate f derivative using 4 floating point operations, compared to the calculation where we have pre-calculated a, and that means that we end up with only 2 floating point operations. So with some reorganization and a little bit thinking, we can actually calculate the derivative with 2 floating point operations instead of 4 floating point operations. And this is something which effectivizes the way we calculate derivatives. So let's now look at the graphical interpretation of what we have. So you will often see automatic differentiation discussed in terms of graphs. And then when you do this in terms of graphs, it's very easy to think of this in terms of a feed-forward neural network. So think of you doing this now. X is fed into A, and A is given by the mathematical function x squared. Then A is fed into B, and B is now giving us the x of x squared, and finally this gives us the final result of f. If we now look at this from a derivative point of view, so we would now have a df of d of x. We could now write this if we now simply use the chain rule. So we would have a df of db, and this is multiplied with a db of d of a. And if we put it like this, we can then multiply it with a dA dx. Now, you could think of these quantities. These quantities don't need to be scalars. They can be vectors, or they can be matrices. And we know that the multiplication of matrices and vectors is something which is given by the associative rule. So that means that I can actually rewrite this in terms of df db and multiplied with db of dA of dA dx. This won't change the result. So whether we have matrices, vectors, or scalars, or tensors, I mean, this is a general rule which is given by the associative rule of multiplication. Now, this has, however, some important consequences for us. Before we go on, we just note one thing, that b is actually equal to f of x. So that means that the derivative you see here is in this case equal to 1. And if we now take the derivative of db dA, which is this quantity here, that gives us simply the exponential with x squared. And then I have dA dx, which is now simply 2 times x. So then we are back to the same equation which we had before. Now, there is an important thing to notice now. And if you look at the graphical representation which we had, you could actually think of that as a kind of neural network where the first one is a hidden layer, the next one is a hidden layer, and then we have f as the output layer. And when we are setting up the derivatives of the unknown parameters, that means the weights and the biases, we're actually going to set up the network, the derivative of the function f with respect to the parameters in terms of all these kind of partial derivatives using the chain rule. So if you look at the term which we have here, this expression, with the first expression, is called the reverse mode. Now, the reason for that is that we begin with the last term here. So we actually calculate, evaluate the derivative at this point which you see here. And then we take the next derivative at this point here, and then we multiply it with the final one, which is actually dA dx. The other formula which we have is called the forward mode. And the forward mode is what we would normally have if we were to think of taking the derivative of the parameters of with respect to the parameters of a neural network if we were to move forward. Now, there are reasons, computational reasons, why we use the reverse mode. One of the reasons for why we use the reverse mode is that when we start iterating and move backward in a network, what we normally have then is that the output has a much lower dimensionality than the input. So if we are going to classify images, for instance, where the input contains 40,000 pixels, 200 times 200, and we only have 10 images, that means we are feeding in 40,000 points, and there will be lots of weights and biases which we need to train when we do the feed forward stage. The matrices will be larger. But then when we come to the final part, we actually start with a matrix of much smaller dimensionality because we have only 10 output variables. And these 10 output variables, they connect with the last hidden layer. And if this last hidden layer has, let's say, 50 nodes, then we simply have 50 times 10 connections. So we would have only 500 weights to train. And that is much less than if we have 40,000 input values, which are then fed into the first hidden layer, which could have, let's say, 100 hidden nodes. Then we would have a matrix of weights, which has dimensionality 40,000 times 100. So when we are starting the training, calculating the derivatives at the endpoint is something which normally implies a much smaller dimensionality. So having huge dimensionalities is also something which can lead to round-off errors. So the hope then is that when we start with a smaller sized problem, is that things like loss of precision, loss of numerical precision, and loss of this kind of the accuracy which we would have in a calculation is perhaps less pronounced when we start from the end of the network. So normally you would then see this reverse mode being favored compared with a forward mode, and specifically for neural networks. Now, when you now look at the model which we had, this is a pretty easy system to calculate, but you can also see the benefit by setting up these derivatives the way we are doing. And if we calculate this kind of intermediate values and can use, and we can set up such a kind of diagram where we feed in X, move to A, move to B, and move to F. This is something which, when the functions become more complicated, can lead to considerable simplifications when it comes to the number of floating point operations. So before we switch back to the Jupyter Notebook and we start looking at the calculation and the setup of a specific neural network, we are going to look at another example of this reverse mode and forward mode calculations. So let's take a look at the second example, which is a little bit more complicated. So let's just call this example 2 here. Let's now suppose that the function f of x has a square root, and it's given by x squared plus the exponential of x squared. So it's pretty similar to what we had before. If we now calculate this in a brute force way, and we assume that one square root is one floating point operation, it's actually not. It requires more floating point operations than the standard arithmetic operations. But let's assume that it's given by just one floating point or just one operation. So we would have the square root. We have x times x, so that's two floating point operations. We have plus here, that's three floating point operations. And then we have x times x, which is another floating point operation. So we had 1 here, 2, 3, 4 here, and then the exponential calculation. So that gives us 5 floating point operations. Now we can obviously now make this easier by simply defining some intermediate quantities. So we could define a, which is x squared, and again we define b, which is the exponential of a, x squared, and then we could define a function which is c, which is a plus b. And finally we can define a function d, which is just the square root of c, which is again the same as f of x. So if you now look at the quantities which we have here, what we end up with then is something which now contains less floating point operations, because if we now define this quantity which we have here, a, this is just one floating point operation. We define this quantity here, that's another floating point operation. And then we have a plus b, so that is the plus sign here, so that gives us 3 floating point operations. And then we have the square root of c, so that's 4 floating point operations. So we actually reduce the calculation of the function f by 1 floating point operation. And if the function becomes more complicated, this obviously is going to require many more floating point operations. Now if I calculate the derivative, so d of f of d of x, this is going to be equal to x times 1 plus the exponential of x squared. There's a division, and this division is actually given by x squared plus the exponential of x squared. Now again, if we do this in a brute force way, we are going to have one multiplication, so that's one floating point operation, one addition here, that's one floating point operation, and then we have, so that is 2, and then we have this one, which gives another one, and then the exponential. So in the numerator we have 4 floating point operations. We have a division here, so that gives us another one, so now we have 5, just the numerator and the division. So we have, if we just write it down here, we have 5 till we reach this point. And then if we go back to the denominator, we have 1 floating point operation, 1 floating point operation, the exponential plus this one, so this is 4, the square root is 5. So that gives us 10 floating point operations if we do it this way, just without thinking. Now if we now use the simpler formula, what we would have is that this is also equal to, and then in this case we would now have x, and we have 1 plus this quantity b, which is pre-calculated. So we already calculated that one in order to calculate the value of the function. And then we have the square root of c of a plus b. So this is actually x of 1 plus b divided by the square root of c. So the square root of c is something which is now simply given by x of 1 plus b divided by d. So d has already been pre-calculated, b has been pre-calculated. We need to have x times 1 plus b. So what we have in this case is now 1 floating point operation, 1 floating point, that's 2. Then a division by d, so we have actually reduced from 10 floating point operations to 3 floating point operations. Now keep in mind another thing is that in this case we have not included memory reads and memory writes. They can vary from system to system. But you see now that for the calculation of the derivatives, if we were not to think and simply calculate a derivative like this, as it would come out from a symbolic manipulation, we would have 10 floating point operations. If on the other hand, and this is the way it's going to be evaluated if I do automatic differentiation, with automatic differentiation, I can actually reduce the calculation of the derivatives down to 3 floating point operations. And that's really fantastic. So now let's see how we would actually calculate these derivatives when we implement automatic differentiation. So the easiest way to see this is now to make a graph. So if we now start with a graph, and you will see this again is going to mimic the way we deal with neural networks. So we have the value of x, and we pre-calculate the value of a. So it feeds into a, which is actually x squared. So we perform the squaring operation. Then this now feeds into the calculation of b, which is actually exp of a. And it goes down again, and we have a plus operation. So we have to indicate that with a plus here. And that feeds into the variable c. Remember now that c is given by a plus b. And this again feeds into with the square root operation. So we would then have the squaring. So I'm just putting up like this. So it feeds into d by a square root of c. And this is the same as f. So in our case, f of x is actually equal to d. Now we need some intermediate calculations now, where we are going to apply the chain rule. So what we would need then, if we now look at partial derivatives, so we would have a dA d of x, which is simply equal to 2x. And then if I look at my dB of d of x, this is actually equal to dB d of a dA of d of x, and that's pretty obvious. We need another intermediate result. So if we look at dC d of x, that's going to be given by dC dA of d of x, and we know that dC with respect to a is equal to 1. And then we have a dB of dC of dB of d of x, because c depends on both a and b, and a and b depend on x. And finally, and if you look at this term here, this dB dx, this term is something which we can rewrite in terms of the previous term. So we have this term up here. So we can actually rewrite it in terms of a dC of dB of dB dA of dA of d of x. So that's that term. And then we can do the same with d of d. d of dc. And that's simply going to be equal to 1 over 2 times the square root of c. And then I have that my d of x is going to be the same as d of dc of d of x. And this is the same as d of f d of x. This is the derivative we want to have here. Now, you see now that in these calculations here, we already have the value for dc of x here. So repeated application of the chain rule is something which is going to give us the derivatives. So what you could do now is to look at the feed or the reverse mode. So you can actually compute the, if we now move on and look at the computation in reverse mode. What we need then is actually to start with so df d of d is equal to 1, because d is equal to f. So the quantity which we need to calculate now is df of dc. and that is equal to a df of dd of dd of dc. And we know that the first term here, this term is simply 1 because f is equal to d. And this term, which we have here, is 1 over 2 over square root of c. Then, if I now take the further reverse mode and I take df of db, this is the same as df of dc. So I'm just using the chain rule, and this is exactly the same way we would propagate backward the derivatives using the backpropagation algorithm for a neural network. And it's easy to see the link here with a neural network without us going too much into details. Simply, if you now draw a graph here, so you could think of f as your output, d is your output layer, c is the layer before, and then b and a are intermediate layers, which add up to conspire to the value c, which then add to the value of d when you take the square root. And then you have x as the input layer. So this kind of calculating derivatives is in essentially the same philosophy as we are applying when we do the backpropagation algorithm. So reverse mode in automatic differentiation is the same as the backpropagation algorithm. So if we do this now, we would have a df dc of db, which we have calculated, which is actually equal to 1 over 2 times square root of c, because dc of db, that is equal to 1, because c is equal to a plus b, so the derivative of c with respect to b is equal to 1. So now we see that df db is equal to 1 over square root of c. If I then look at df, so I'm going further backward, so I can reapply the chain rule again. So I have a df db, db da, and we know the value of db da because that's just the exponential of a, plus a d of f of dc multiplied with dc of d of a. So that quantity, this quantity which we have here, is obviously the quantity which we need to look at. So that this is df db, we already calculated that one, so this is equal to 1 over 2 times square root of c. This term here is the same as e exponential of a, which is x squared. And then this term here, df dc, is a quantity which we already calculated. So this quantity here is 1 over 2 square root of c, and dc da is equal to 1. So what we have then is that this quantity is 1 over 2 square root of c, and then I have 1 plus the exponential of a, and this is simply 1 over 2 square root of c of 1 plus the quantity b, which we again can write as 1 over 2 times d, or 1 plus b here. Then the final step, which we need now, is actually when we backpropagate again. So we are now at the derivative at a. So we did df dA. So we've been backpropagating the derivative of f till we reach a. And then the final stage is actually df dx. So we can now, by backpropagating here, we get the final value of d of f d of x, which is simply equal to df dA, again using the chain rule, of dA dx, which again, when we plug everything in here from the previous calculation, this is the same as 2 times x divided 2 times d multiplied with 1 plus b, and this is equal to x multiplied with 1 plus b, which is pre-calculated, and also d, which has been pre-calculated. So with the backpropagation or reverse mode using the chain rule, we can then reach the correct value for the derivative by starting with the output and then backpropagating ourselves in this diagram which we drew up here. So you could say now that the automatic differentiation actually relies on you being able to split the operations in these different stages, and then by repeated application of the chain rules, you can actually reach the last part here. And in our case, we would now replace the x's with the x's and the parameters theta. And we would simply be interested in the parameters theta. So we will backpropagate or do the reverse mode and get the derivatives of our neural network in terms of all the previous parameters. So last week, when we did these exercises, we found the final expressions for the backpropagation algorithm, which we need to code. And this is what we need to discuss in the next session. So if we look at the backpropagation algorithm, so let's just quickly repeat it because we derived it last week. So let's set up the backpropagation equations. Propagation equations. So what we defined was the parameter delta J in the final layer. So we took a delta J in layer L, this is the final layer, which was given by the derivative of the activation function in this final layer. And this had as input this Zg of L. And this is multiplied with the derivative of the cost function with respect to the output in the final layer. So with this intermediate quantity, we could then define further quantities. So we could then find the derivatives of the cost function with respect to the weights. And now we are putting the subscripts. So we would have weights jk in the final layer. And these are given by delta j, this parameter delta j, multiplied with the input from layer L minus 1. What we also found is that these parameters, delta j of L, are parameters which we can also define in terms of the derivative with respect to the biases, J of L. So what we have now are the derivatives of the quantities which we need to evaluate at the final layer. This is the output layer. And then this would correspond to the same thing as we did here when we got the answers df of d. And then we would propagate one step behind. So df of d here is actually equal to 1 in this specific case. And then we need the derivative in the step behind, which when we look at the graph here, would now correspond to this quantity. So we start here, calculate the derivative with respect to that one, and d is equal to f by definition in this simple example. And then we propagate back to c, and then we get the derivative with respect to c here. And then we get the derivative with respect to b. And finally we get it with respect to a, and that means that we propagate it through the whole network till we calculate this one. And this is essentially what we end up doing when we deal with neural networks. And the only quantity which we needed in addition then was the delta J at the layer L. And this is where we would compute the values in previous layers of L plus 1, the layer ahead, multiplied with the weights from the layer ahead, L plus 1, and then the derivative of this activation function, which we sometimes call for f and sometimes call for sigma. So these are the derivatives with an input set g of L. So when we are setting up the algorithm now, we need to start with an initial value. We need to set up the architecture of the network. We need to define activation functions. We need to define the number of hidden layers, the number of hidden nodes. We need to define the cost function, the gradient approximation, the learning rate, all the parameters which we sketched at the very beginning. So this is a typical example on how we would set up a neural network. And the thing which is in a way underestimated, as we mentioned, is the fact that automatic differentiation has two modes, reverse mode and forward mode, and the backpropagation algorithm is actually just the implementation of the reverse mode. And this gives normally a smaller dimensionality when we start propagating backward the different parameters. Now this leads when we have these equations, we can then set up a scheme for updating the derivatives. So what we get then, when we have all these steps, is that for each layer, then for each layer, what we have then, we have the following. So we could now set up a loop here with L, where we start with L minus 1, we do L minus 2, and then we reach an intermediate level until we reach the final hidden layer, which we would call layer number 1. And in that specific case, we would now set up the calculation of this quantity delta J of L. And when we have delta J of L, then we can update the, because delta J of L is going to give us the derivatives. As you can see here now, the derivatives of the cost function, when we now replace the derivatives with a given layer L, lowercase l, it's going to be given by delta J of L and multiplied with AK L minus 1. And we are going to have a similar expression for delta B of J. So it means that we can then update the algorithms. So we find that one, we compute this quantity, and then we have an update scheme where we now have a Wj of K of layer L, and this is updated using the previous value. So we start with a guess, obviously, minus, and then we have a learning rate. And this is, again, one of the big parameters and the big problems in neural network calculations. And then we have a delta JL, and this is multiplied with AK of L minus 1. So this is the gradient. This term which you see here is the gradient in layer L. And then we need a similar one for B of J of L. And this is being updated by the previous value, Bj of L, minus, and then we have the learning rate, and multiplied with delta J of L. And then we would continue this iterative process. So one iteration is us performing a feed-forward pass and a backward pass. So one iteration here consists of a feed-forward pass and a back propagation pass. And I just write this as a back prop pass. And then you will continue till the cost function which we have, which we want to optimize, till this cost function has reached a value which we are happy with, till cost function converges. So with convergence, it means that we cannot squeeze in more accuracy in the model which we have, till cost function converges to a specific value. So suppose now we want to have if you're performing a linear regression type of neural network calculation, now it's no longer linear regression, it's actually just a regression problem. And we are trying to fit a function or some data points with a neural network. And then we could say that ideally we would like to have this error to be 10 to the minus 6 as an example. And then we would like to iterate till we have reached this value. Now, what this would imply is that we would have to make many calculations where we would try to fit learning rates, where we would try to adjust number of batches, we would try to adjust the number of hidden layers, the number of hidden nodes, etc., etc. So going back to the model, we have the architecture, and then we have the optimization part of the model. So these are the important ingredients which we now have on paper, and with that we are now ready to look into the setup of a neural network. And what we are going to do now is to look at a classification problem because this is also relevant for project number 2. But in project number 2, we are simply going to look at a binary case. The examples in the lectures are going to deal with a 10 class problem. We are going to look at 10 numbers. So this is a so-called MNIST dataset, which is widely used in machine learning applications and machine learning studies. So you're going to encounter that database many, many times. But in project number 2, we are mainly going to deal with a binary case, and we are going to look at this cancer data where we can have either a benign tumor or a malignant tumor. So that's an example of just a binary case. And then in project number 2, we are also going to look at the fitting of a function or fitting of the data which we have in terms of a neural network. Now, when we are going to fit a neural network to some specific function, you could feel tempted to repeat what you did in project number 1 and just feed in a design matrix in terms of a polynomial approximation. Now, the neural network, what that will do then is try to find the optimal parameters which fit, let's say, a fifth order polynomial to your data. Your data may not be represented by a fifth order polynomial. So the philosophy of neural networks is actually, when we follow the universal approximation theorem, is that the network should actually try to find the best possible parameters which represent a given function. And that may not be a fifth order polynomial. So you could try this in project number 2 to feed in a design matrix like you did in project number 1, or you can just feed in, if you're dealing with a one-dimensional function, you could just feed in the input values x. If you're dealing with a two-dimensional function, you could just feed in the values x and y. And then simply let the neural network find the best possible representation with that specific input and the specific output, which could be the Franke function, or it could be just topographic data, like those which you studied in project number 1, or it could be another type of function. So now we are basically ready to move into the setup of a program. And in the next lecture, we are going to look at the setup of a program which allows us to define a neural network with a certain flexibility. We can have a given number of hidden layers, we can change activation functions, etc., etc. And then we, in the case of linear regression, we have to define quantities like the output activation functions. For linear regression, us fitting a function, we normally just let the output be equal to the output from the last hidden layer. So the output from the output layer is not modulated by a specific activation function. That is common when you do a regression type problem. When you're dealing with a classification type problem, you would modulate the output with a given output function. And that could be a sigmoid in case of a binary problem. It could be a so-called softmax function in case of a multi-class classification problem. But we're going to stop here, and our next set of lectures is now going to deal with the calculation of and the setup of a neural network applied to a classification problem. And then after we're done with that, we are going to look at how we can use neural networks to solve differential equations, which is a very hot research topic and which fits many of you studying natural science. And later we are going to look at how we can simplify the calculation of a neural network using libraries like TensorFlow with an API called Keras, or if somebody wants to use PyTorch, you should feel free to do that. But now we are ready to build our program.